If you remember in our first unit, we created some movement in our parent functions, and so we started moving them around the coordinate plane, either with the shifting to the left or right, or up or down, and then of course we also had the reflection across the axis. And so what we're going to do here is we're just going to formalize those transformations with the rules. And so we've created a rule for the different types of transformations that we're going to deal with. And so what you see here is we've kind of made a nice little table to kind of summarize all these various rules. And so we'll just kind of start with the first box here, and we're dealing with the reflections. Now you can see that if the function is y equals f of x, that the reflection is going to be y equals negative the value of the function, and so that's going to flip it over the x-axis. Now, interestingly enough, we didn't deal with this situation as much, but if you notice that if we negate the x value within the function, it actually reflects it over the y-axis, and in many cases that actually gives us back the same function. And so we briefly spoke about odd and even functions and how they differ in the previous lesson. And so you can see here, if we reflect over the y-axis, sometimes that keeps us the same function, and sometimes that changes the parent function a little bit. So we'll look at that in more detail and examples of that a little bit more in class. Now, so we've had a good introduction to reflections. The second transformation that we've really looked at in detail are translations, and so we've discussed in detail about adding or subtracting values from the entire function. And so we said this takes place outside of the parentheses, if you will, or outside the actual function part. And of course that's going to move the graph up or down, and you can see the example associated with that. Now, if we're embedded inside the function, or what we've said is inside the parentheses, that creates a left or right shift, and of course this is where we talked about the opposite value taking place. And so you can see we add a constant value inside the function that actually shifts it back to the left. And so these are basically, if you recall, our h and our k values, our c's inside and outside. And so we formalize it more with an h and a k so that it's easier to determine. Now, the last one is the one that we did not spend as much time on in Unit 1, and it's because I was kind of saving it for this point in time, and that's a dilation. Now, what a dilation is either a stretching or compressing of the actual graph. Now, the reason I didn't want to get into too much detail about this, and I still really don't want to get into a great amount of detail, but what we're doing here is if we expand a graph vertically, we're stretching it vertically. That has the same net effect as compressing a graph horizontally. So I didn't want you to get caught up in the words compressing or stretching. It just tends to confuse people. And so you can see that if we compress the graph vertically, it has the same net effect as it stretching it horizontally. And so really where I want you to be more concerned is this. In essence, if the c value is greater than 1, regardless of whether we're multiplying it to the whole function or if we're multiplying it inside the function, this is going to give us a steeper looking graph, if you will. And you can see the images of the pinkish looking graphs. That's kind of the effect that we're getting whenever we have a value greater than 1. Now, if our c value is between 0 and 1, so if we have some sort of fractional value for c, what it's doing is creating a flatter image, and you can see the greenish colored images in the pictures are a little bit flatter. Now, depending on whether you're talking about a vertical stretch or compression or a horizontal stretch or compression, it could be different either way, but what I'm more concerned about is if it's greater than 1, it kind of creates a steeper looking graph, and it's fractional, it's a flatter looking graph.